Hi, I'm Yishan Zhang. I'm now a second-year PhD student. Today, I'm really happy to present one of my recent work titled Prelimit Coupling and Steady-State Convergence of Constant-stepsize Nonsmooth Contractive acid. This is a joint work with my excellent collaborators. Lucy Huo, she's a PhD student. Yudong Chen, he's a professor. And Qiaoming Xie, she's my advisor. They're both from the UW Medicine. So in this work, we focus on the stochastic approximation, which aims to approximately find the fixed point derived by the function h. And the algorithm iteratively updates the theta by a noisy observation for the function h. So here we use the W to denote the IID noise, and we use the constant step size to do the iteration. The reason is that the constant step size always leads to a fast convergence rate, and it is easy to implement because there is only one parameter alpha that needs to be tuned, and it will always have a robust performance. So in this work, we focus on the case that H theta can be non-smooth, even not differentiable with respect to the theta. We highlight that this is a very common case because there are many popular algorithms that can be reformulated as a non-smooth SA. For example, the non-smooth SGD and Q-learning algorithms. Then our first result just tells us that the row iterated theta t will finally converge to a limit random variable theta alpha in the persistent distance of order 2. We highlight that by the usage of the constant step size, the convergence rate is geometrically fast. Then our second results tell us that if the function h is smooth, the bias will go to 0 faster than the square root of alpha. And most importantly, if the function h is non-smooth, the bias is exactly proportional to the square root of alpha, which is in sharp contrast with the result for the smooth SA, that the bias is proportional to the alpha. We highlight that for the prior work on the smooth SA, they most depending on such a linearizing method. But in the non-smooth SA, this method is not applicable because the function h theta can be non-differentiable with respect to this theta for the non-smooth SA. Therefore, to overcome this challenge, we propose a new method called the Prelimit coupling method to derive the bias calculation for the non-smooth SA. But before we talk about the technique, let me first give you a big picture about how we derive such a bias calculation for the non-smooth SA. So first, we consider such a square root of alpha scaled iterates denoted by the yt alpha here. And because we have the V-convergence of theta t alpha to the theta alpha, we can also derive the V-convergence for the yt alpha to the y alpha. Then we are curious about that. If when the alpha goes to 0, the y alpha will also converge to some limit distribution y, and we call this result as the steady-state convergence result. So why we curious about this result is because if the steady-state convergence holds for the y alpha, that means that if the expectation of y alpha will also converge to the expectation of y. And by the definition of y alpha, and by a very basic calculation, we can finally obtain the second equation here. That is exactly what we want for the bias calculation. And then by our Prelimit, and then we go to our Prelimit coupling technique that applies the coupling to the Prelimit random variables yt alpha with finite and may potentially different steps as alpha and a different time step t. And recall that our goal is to establish the steady-state convergence that the y alpha will converge to y in the persistent distance of order 2. So finally, by our Prelimit coupling technique, we obtain the theorem 3 that the y alpha will converge to y. And sequentially, we will have the second equation here, which is what we want for the bias calculation. Thanks.